Welcome. Today we're diving into the fascinating world of clustering methods, a key concept in both supervised and unsupervised learning. Clustering is all about grouping data points so that those in the same group or cluster are more similar to each other than to those in other groups. This technique is widely used in data analysis, pattern recognition, and machine learning. Whether you're sorting customers by purchasing behavior or organizing images by content, clustering helps make sense of complex data. Let's start by understanding what clustering really means and why it's so important in the field of machine learning. Clustering is a fundamental process in machine learning, often used to discover hidden patterns in data. It's especially valuable when you don't have labeled data, allowing you to find structure in what might seem like chaos. By grouping similar data points together, clustering can reveal insights that might otherwise go unnoticed. This process is not only crucial for data exploration, but also for tasks like anomaly detection and data compression. As we move forward, we'll see how clustering fits into both supervised and unsupervised learning frameworks. Before we delve deeper, let's clarify the difference between supervised and unsupervised learning. In supervised learning, we work with labeled data, meaning each input comes with a corresponding output. The model learns to predict outcomes based on these examples. In contrast, unsupervised learning deals with unlabeled data. Here, the model tries to find patterns or groupings without any prior knowledge of the outcomes. Clustering is a classic example of unsupervised learning, but it can also play a role in supervised scenarios, as we'll see. Clustering is the process of dividing a dataset into groups or clusters, where data points in the same cluster are more similar to each other than to those in other clusters. The goal is to maximize the similarity within clusters and minimize it between clusters. This technique is widely used in customer segmentation, image analysis, and even in organizing search results. By identifying natural groupings in data, clustering helps us understand the underlying structure and make informed decisions. There are several types of clustering methods, each with its own strengths and weaknesses. The most common include partitioning methods like k-means, hierarchical methods, density-based methods such as DBCN, and model-based approaches. Each method uses a different strategy to group data points, depending on the nature of the data and the desired outcome. Understanding these methods is key to choosing the right approach for your specific problem. K-means is perhaps the most popular clustering algorithm. It works by dividing data into a predefined number of clusters, called K. The algorithm assigns each data point to the nearest cluster center, then recalculates the centers based on the assigned points. This process repeats until the clusters stabilize. K-means is fast and efficient, making it ideal for large datasets. However, it requires you to specify the number of clusters in advance, which can be a limitation in some cases. Hierarchical clustering builds a tree of clusters, starting with each data point as its own cluster, and merging the closest pair step by step. This results in a hierarchy or dendrogram that shows how clusters are nested within each other. You can choose the level of granularity by cutting the tree at different heights. Hierarchical clustering is useful when you want to explore data at multiple levels of detail, but it can be computationally intensive for large datasets. Density-based clustering methods, like DBCN, group data points that are closely packed together, marking points in low-density regions as outliers. This approach is great for finding clusters of arbitrary shape and handling noise in the data. Unlike k-means, you don't need to specify the number of clusters beforehand. Density-based methods are particularly useful in applications like anomaly detection and spatial data analysis. Model-based clustering assumes that the data is generated from a mixture of underlying probability distributions. Gaussian mixture models, GMM, are a common example where each cluster is represented by a Gaussian distribution. The algorithm estimates the parameters of these distributions to best fit the data. Model-based methods can handle complex cluster shapes and provide probabilistic assignments, but they may require more computational resources. Clustering is most commonly associated with unsupervised learning, where the goal is to find structure in unlabeled data. Since there are no predefined categories, clustering helps uncover natural groupings based on similarities. This is especially useful in exploratory data analysis, where you want to understand the underlying patterns without any prior assumptions. Unsupervised clustering is widely used in fields like marketing, biology, and image processing. Clustering is primarily an unsupervised technique. It can also play a role in supervised learning. For example, clustering can be used as a pre-processing step to create new features or to group similar instances before applying a supervised algorithm. This can improve the performance of classification or regression models by capturing hidden structure in the data. In some cases, clustering helps identify mislabeled data or outliers that could affect model accuracy. Clustering has a wide range of applications across industries. In marketing, it's used for customer segmentation, helping businesses tailor their strategies to different groups. In healthcare, clustering can identify patient subgroups with similar symptoms or treatment responses. It's also used in image analysis, document organization, and even in detecting fraudulent transactions. The versatility of clustering makes it a powerful tool for extracting value from data. Imagine a retail company wanting to understand its customers better. By applying clustering, they can group customers based on purchasing behavior, preferences, and demographics. This allows the company to design targeted marketing campaigns, improve customer satisfaction, and increase sales. Clustering helps businesses move from a one-size-fits-all approach to personalized strategies that resonate with different customer groups. Image processing, clustering is used to segment images into regions with similar characteristics. For example, in medical imaging, clustering can help identify different tissue types or detect abnormalities. By grouping pixels with similar color or intensity, clustering simplifies complex images and makes it easier to analyze and interpret visual data. This technique is essential in fields like computer vision and medical diagnostics. Clustering is also used to organize large collections of documents. By grouping similar documents together, it becomes easier to manage, search, and retrieve information. This is particularly useful in libraries, news agencies, and online platforms with vast amounts of text data. Clustering helps automate the process of categorizing and indexing documents, saving time and improving efficiency. Clustering can help identify anomalies or outliers in data. By grouping normal data points together, it becomes easier to spot those that don't fit any cluster. This is valuable in fraud detection, network security, and quality control. Detecting anomalies early can prevent financial losses, security breaches, and ensure product quality. Clustering provides a powerful tool for monitoring and maintaining data integrity. Another application of clustering is data compression. By representing groups of similar data points with a single representative, clustering reduces the amount of data that needs to be stored or transmitted. This is especially useful in image and video compression, where similar pixels or frames can be grouped together. Data compression helps save storage space and speeds up data transmission, making it essential for efficient data management. Clustering can be used to create new features for supervised learning models. By assigning cluster labels to data points, you can add these as additional features, capturing hidden structure in the data. This can improve model performance by providing more informative inputs. Feature engineering with clustering is a powerful way to enhance the predictive power of machine learning models. Clustering is often used as a pre-processing step in machine learning pipelines. By grouping similar instances, you can simplify the data, remove noise, and identify patterns before applying more complex algorithms. Pre-processing with clustering can lead to better model performance and more interpretable results. It's a valuable tool for preparing data for analysis and modeling. Evaluating the quality of clustering results can be challenging, especially without labeled data. Common metrics include silhouette score, Davies-Bouldin index, and within cluster sum of squares. These metrics assess how well the clusters are separated and how compact they are. Choosing the right evaluation method depends on the specific application and the nature of the data. Clustering is a powerful technique, but it comes with its own set of challenges. Choosing the right number of clusters, dealing with high-dimensional data, and handling noise or outliers can be difficult. Different algorithms may produce different results on the same data, making it important to experiment and validate your approach. Understanding these challenges is key to successful clustering. Selecting the appropriate clustering method depends on your data and goals. K-means is great for large, well-separated clusters, while hierarchical methods are better for exploring nested structures. Density-based methods excel at finding irregular shapes and handling noise. Model-based approaches are ideal for complex, overlapping clusters. Consider the characteristics of your data and the requirements of your application when choosing a method. Scalability is an important consideration when working with large datasets. Some clustering algorithms like K-means are highly scalable and can handle millions of data points efficiently. Others, like hierarchical clustering, may struggle with very large datasets due to their computational complexity. It's important to choose an algorithm that can scale to your data size without compromising performance. High-dimensional data presents unique challenges for clustering. As the number of features increases, it becomes harder to measure similarity and distinguish clusters. Techniques like dimensionality reduction, such as principal component analysis (PCA), can help simplify the data and improve clustering performance. Handling high-dimensional data effectively is crucial for accurate and meaningful clustering results. While many clustering algorithms are designed for numerical data, there are methods for clustering categorical data as well. Algorithms like K-modes and hierarchical clustering with appropriate distance measures can handle categorical variables. It's important to choose the right algorithm and similarity measure based on the type of data you're working with. Visualization is a powerful way to interpret and communicate clustering results. Techniques like scatter plots, dendrograms, and heat maps can help you understand the structure of your clusters and identify patterns. Effective visualization makes it easier to explain your findings to others and make data-driven decisions. Clustering is an essential tool for exploratory data analysis. By grouping similar data points, you can uncover hidden patterns, relationships, and trends in your data. This helps guide further analysis and informs decision-making. Clustering is often the first step in understanding complex datasets and identifying areas for deeper investigation. Clustering can be combined with other machine learning methods to enhance results. For example, you can use clustering to pre-process data before classification or regression, or to identify subgroups for targeted modeling. Combining clustering with dimensionality reduction, feature selection, or ensemble methods can lead to more robust and accurate models. With the rise of big data, clustering methods have evolved to handle massive datasets. Distributed and parallel algorithms, such as those implemented in Apache Spark, allow clustering to scale across multiple machines. This enables analysis of data at unprecedented scale, opening up new possibilities for discovery and innovation. As with any data-driven technique, ethical considerations are important in clustering. It's essential to ensure that clustering does not reinforce biases or lead to unfair treatment of individuals. Transparency, fairness, and accountability should guide the use of clustering in sensitive applications like hearing, lending, or healthcare. Responsible use of clustering builds trust and ensures positive outcomes. Clustering methods continue to evolve, driven by advances in machine learning and artificial intelligence. New algorithms are being developed to handle more complex data, improve scalability, and provide better interpretability. The future of clustering promises even greater insights and applications across diverse fields, from personalized medicine to smart cities. Real-world projects, clustering is often used alongside other data analysis techniques. For example, in e-commerce, clustering helps segment products and customers for personalized recommendations. In transportation, it's used to analyze traffic patterns and optimize routes. The practical value of clustering lies in its ability to turn raw data into actionable insights. Personalization is a major trend in today's digital world, and clustering plays a key role. By grouping users based on behavior, preferences, or demographics, companies can deliver tailored experiences, recommendations, and content. This enhances user satisfaction and drives engagement, making clustering a cornerstone of modern personalization strategies. In healthcare, clustering is used to identify patient subgroups, predict disease outbreaks, and personalize treatment plans. By analyzing patient data, clustering can reveal patterns that inform diagnosis and improve outcomes. It's a valuable tool for researchers, clinicians, and policymakers working to advance healthcare delivery. Financial institutions use clustering to detect fraudulent transactions, assess credit risk, and segment customers. By grouping similar transactions or clients, clustering helps identify unusual patterns and improve decision-making. It's an essential technique for managing risk and optimizing financial services. Marketing teams rely on clustering to segment markets, understand customer needs, and design targeted campaigns. By analyzing customer data, clustering reveals distinct groups with shared characteristics. This enables marketers to craft messages and offers that resonate with each segment, boosting engagement and sales. Social networks use clustering to detect communities, recommend friends, and analyze user behavior. By grouping users with similar interests or connections, clustering helps platforms deliver relevant content and foster engagement. It's a key technique for understanding and managing large, complex social graphs. In biology, clustering is used to group genes, proteins, or organisms based on similarities. This helps researchers understand evolutionary relationships, identify disease subtypes, and discover new biological patterns. Clustering is a fundamental tool in genomics, proteomics, and ecological studies. Image recognition systems use clustering to group similar images, detect objects, and organize large image databases. By identifying patterns in visual data, clustering improves the accuracy and efficiency of image search and classification. It's a vital component of modern computer vision applications. Text mining applications use clustering to group similar documents, extract topics, and organize information. This helps automate the process of sorting and summarizing large volumes of text, making it easier to find relevant information and gain insights from unstructured data. Recommendation systems use clustering to group users or items with similar preferences. This enables personalized recommendations, improving user experience and increasing engagement. Clustering helps recommendation engines scale to large datasets and deliver relevant suggestions efficiently. Clustering can be applied to time series data to group similar patterns or trends. This is useful in fields like finance, meteorology, and manufacturing, where understanding temporal patterns is crucial. Clustering helps identify recurring behaviors, anomalies, and seasonal effects in time-based data. Spatial data analysis uses clustering to identify regions with similar characteristics, such as crime hotspots or disease outbreaks. By grouping locations based on attributes, clustering supports decision-making in urban planning, public health, and environmental monitoring. Network analysis applies clustering to group nodes with similar connections or roles. This helps uncover communities, detect influential nodes, and analyze network structure. Clustering is widely used in social network analysis, telecommunications, and biological networks. Wrap up, clustering is a versatile and powerful technique in both supervised and unsupervised learning. It helps uncover hidden patterns, organize data, and drive better decision-making across a wide range of applications. Whether you're working with customer data, images, or networks, understanding clustering methods will empower you to extract more value from your data. Keep exploring and experimenting with different clustering techniques to find the best fit for your needs.